mixer. Please welcome Keith Luke.
Hi. You know, yesterday I spoke and actually people in the room again. Very pleased that people actually came back. Thank you. One of the people that I spoke to yesterday suggested that I show the screw because I hadn't actually shown it. It was confusing without actually showing it. So I had photographed it, and we'll look at that again today. And I actually have it sort of turning so that you can look at it while it's going. This was kind of spur of the moment since it only happened yesterday, so these aren't very professionally done, but I think you'll get the general point. When I was young, one of the things my father and I did was to watch science fiction movies together. And this was one of my favorites for a particular reason. I mean, it's got boys, girls, robots, monsters, great stuff. But there are other reasons why it's my favorite. You know, I mean, how can you go wrong with spaceships, robots? But down here, whoops. There was a particular passage right in here where this guy is talking about all these gauges. So there's an alien race that has created all this power on this planet. And what he talks about is interesting because what he talks about on all these gauges is how many amps they draw. And each one is set in decimal series. Each division recording exactly 10 times as many amps as the one preceding it.
As the one preceding it. 10 times 10 times 10 times 10 times 10 times 10, on and on and on, row after row, gauge after gauge.
Almost to the power of infinity. Now, if you've got a mixer that can do that kind of thing, not amperage-wise, but where you're multiplying a lot on each mixer. If you can do 10 times 10, that's great. But if the mixer itself has 10 times 10 times 10, and you've got a bunch of mixers, that's a lot of mixing. I mean, it doesn't take very astute math to go 100. Next one is more than 1,000. You just keep going very fast. I think that's what's happening in this mixer. Yesterday I asked if water vapor is well mixed in undried pellets. What exactly is water vapor? It's a molecule separated from other molecules of the water, other H2Os. But it's a vapor. Where is it in these molecules? You know, hydroscopic material, where is it? Is it in the polymer? The people I ask tell me it's between the polymers, space between the polymers. Suppose you keep it there. Suppose you never let it out. Well, if it never gets out of the space between the molecules, it does never agglomerate. If it doesn't agglomerate, it doesn't become water, and maybe that never bothers you again. I put this up every time because it's important. What is the goal of mixing? How do we want to think back? If I were on Star Trek, right, we would just get a replicator. Right? Be no big deal. We just put one atom, big atom, small atom, big atom, and we do that three-dimensionally. We don't have that. But we'd like to start to approach it in plastics with both big and small molecules. Now, if you were going to do that, how could you do it? Well, you would need a very orderly system. You can't just throw disorder at things. That doesn't mix. If you took the crystal and threw disorder at it, it wouldn't be as perfect. we've got some really good mixers. They've been around for a long time. This is a counter-rotating one, and it's a fairly orderly mixer. Right in here, the material gets trapped between, it's a C shape, it gets trapped between here and here. But all the material that's in there is treated the same way. It all goes down here and starts to get milled. So all of that is treated the same. That makes it an orderly mixer, which is good. Now, it just stays there, right? As it goes down, it moves down the screw, sure, but is there any 10 times 10 times 10 times 10 to this? I don't see how, I don't see where. It's a very good dispersive mixer though. It has problems, of course, but what doesn't?
Oh,
We've got co-rotating twins. These are excellent mixers. They're more, they're distributive and dispersive to some degree. We talked about yesterday how the forces between the screws here, the red indicates one thing, yellow indicates another mixing, and meanwhile, what's happening? All this material in the green tends to go, well, past it. We're not mixing 100% of this. I did an experiment one time with some twin screw friends of mine. I took them out for beer. And after I gave them enough beers, I then asked the question, how much of what goes through here never gets mixed? It never sees that elongation. After enough beers, they told me, maybe 4%. Now, 4% is a lot. When you start talking about a tensile bar, where you've got 4% error here or there, I mean, if you've got 4% dirt, where will it fail? Well, it'll fail to dirt. If you've got 4% of holes, because you've got residual monomer, and they're all aggregated together, where will it fail? So the problem with this one, from an orderliness, from a method point of view, right, is you're splitting the mass. Some of it's being treated here, some of it here. It's not a distributed mixer in terms of its evenness. We would like all the material to be treated exactly the same way. We have uneven dispersion forces. So this one is not a particularly orderly mixer. We looked at this yesterday. We said a single screws mixing is, well, we feed it, we melt it, we get it out here, and then some marginal things happen. I mean, we can call it mixing. I mean, the material actually mixes here, the material in the center of this goes forward faster than this. But how many spirals do you get per LD? One. If you have a 10 LD heat ring section, you've got 10 spirals. It's not a lot of spiral, not a lot of mixing. Suppose you do something different, radically different. Suppose that you put another, you can't call it a flake, you call it a pump. Why is it a pump? Because if you put your hand in here, it's going to get caught and go that way. The same is true for the polymer. It's grabbed up here by the barrel, it's resisted down here, but if you've got a melted ball here, it pumps that out. There's nothing over here, it's empty. What we want to do is to keep this material on the side, just on the side of the flight, so its resistance is very low. Okay, how many times does that go around? Well, it's not that tough. Let's suppose that this diameter is 180 thousandths. And you've got the barrel going by. Let's suppose you've got a 1-inch extruder. Basically 1 times the perimeter, so it's pi. So you take that 180, and you divide it into 3.14, and you get about 17 spirals when it's that big. At this end, when it's the smallest. Why is it the smallest? Well, eventually there's clearance over P. So the clearance will be 40 thousandths in this case. Well, now you take 3.14 and divide it by 40 thousandths. Now, how many spirals do you have down there? 78, if my memory is correct. Well, you know, how long is this? This is roughly 2 LDs long. If you fill it up that much, it's a 1-inch extruder, that's 1.5 inches long. Well, that's a lot of spirals. Now, the other thing that happens is also interesting, because we're looking for mixing. What kind of mixing would we like? Would it be helpful if you turned this inside out, for example? What would happen to your temperatures? I mean, we always talk about temperature uniformity. Don't forget when you're mixing that you're mixing temperatures. Right? Well, the outside of this gets carted away by a P1. The inside of this is going down here. So the outside is going to go this way. That's interesting, because it gets stretched next. It's all axial. There's no pressure flow here. It's just dragged along that P1 plate. What we know is here. We know that this thin film is about 1.4 mils in the test that we've done, and that's a millimeter. Well, you start with, 40 thousandths, you go to 1.4, well, that's more than an order of magnitude reduction. So how many spirals did we just have? A lot, a whole lot. That's all happening here. The drag here is the lowest possible drag you can have, because you're not pushing stuff through, you're just dragging it. There's no pressure flow here, nothing pushes. When it leaves C2, it winds up over here. So a little bit comes through first, because the pump is the same all the way across. So this shape is the inversion of this one. But now what happens to your outside flow? The outside stuff went this way and arrives here and becomes the inside. So temperature-wise, you've inverted that. Now, let's see. Outside became inside. What happens when it goes over here? Inside becomes outside. You're going to keep moving it back and forth inside to outside while you have all this spiraling, which is how much did we say? Well, you put these two together, you add them up, right? So it's 78 plus 17 over here, that's 95. Right? You've got 78 over here plus 17, that's 95. It's very orderly. But 95, that's 2 orders of magnitude of spiraling in an inch and a half on a 1-inch machine. So if you've got 2 orders of magnitude, here in spiraling, and 1 point, that's a lot. That's 2 orders of magnitude. So you're talking about a kind of a new mixer. What I'm suggesting is that you get 100 times better mixing than you do in the conventional metering section on a 1-inch extruder, where in that kind of an LD you might get 1. So it's 100 times better. This goes into another one. And that one's 100 times better. And there are a total of 7 mixers on this screw. That gets you down to a ridiculously small size. And it's all very orderly. Talked about this yesterday. What I want to just point out is that this is a significant effect. Forget about the oil. Just think about all that layering that takes place over here. Layering creates impact resistance. So, what do these screws look like? All right. Whoops. So here's the entire screw. It's a 36-to-1. People got confused as to where things are. Well, let's make it clear. Basically, what you've got here is a typical solids conveying preheating situation. Where is the C1 channel? It's right there. It's that big one. That's this channel. The material's going to move over P, right, which is this right here. it just looks like a flake, but now it's a pump because we haven't filled all this. So this is where we're going to get planar shear without pushing stuff through. We're not going to raise the temperatures any more here than we have to. Then we're going to get that stretching. And that stretching takes place over C2, right here. That's C2, and then in the back here you can just barely see the beginning of the channel, which is C3. But when you move down a little bit further, what happens? All of this empties out and comes around here and starts all over again. So nothing happens to it between those two. It is a direct input from one to the next. This is where it's not really professional, because everybody plan on doing it. But let's rotate this through and see what happens. What did I do?
You made it go dark.
I made it go dark. Thank you, Jim. I didn't think it was
Okay,
possible
start
to
the
do that.
rotation. And zoom in. Start at the beginning of the screen. Solids conveying, preheating. First mixing element designed for solids. Feeds directly here into the second mixing element. Smooth transition, which then feeds directly into the third element. All widely spaced to make sure that there is no solids compaction. Followed by the fourth and fifth mixing elements, which are smaller.
Shorter, not smaller.
Assumption being that everything is melted down. Last two, followed by the detachable metering section. And Tony, who's concentrating?
Well, as I said, I hadn't planned on showing that video. But I think it does give you, I think, a different idea. Chris, you have a question? You want to see it again?
It helps to see the real thing, yeah.
Okay.
Yeah.
Anybody want to see it again? All right. So, these are the materials that we've tested so far with the molecular homogenizers. And in all these cases, you just put material in, undried, and it comes out without any bubbles. Now, it's hard to figure out exactly how that happens. But if you're keeping individual water vapor molecules as vapor between the molecules, in the air between the molecules, then if you don't get the water back together, it's reasonable to think that they never become bubbles that you can see. And they might be the same kind of bubbles that you have here in the air, which we don't really care about. Or you could say that the pellets themselves are a microfoam before you dry them, because they've got water vapor in them, and they're distributed very well. Now, one of the things I didn't touch on yesterday was the pressure variation. I mean, it doesn't do you any good at all, to have an extruder that surges continuously. It's much better if your pressures are uniform. Right? So, some years ago, we did some work on accumulators, and these are similar. The accumulators that we worked with then were small accumulators. But, you saw how big that C1 channel is? It's literally large compared to the size of pellets. That's on a small extruder. So let's say that you have a little more feed by accident, that 12 pellets drop in instead of 8 pellets, which on a small machine is what's going to happen. What's going to happen here? Well, the fill length is going to change. And when it gets back to 8 pellets, 12 pellets, it'll just go back and forth here. Right? Well, when that happens, it's not arriving out here in C3 right away. It takes some time. You look at the length of that arrow compared to these arrows, it takes a little extra time. This then, whoops. This whole section here acts as a rather large accumulator. Now, you've got 7 accumulators here, each one reducing the pressure variation as you go down. So I thought I would show you, what can happen. But typically the pressure on these things, all the ones we've run so far, we can easily induce plus or minus about 30 pounds barrel pressure at the end of the screw, which is quite good. I want to show you how insensitive this process is, how good the screw is, which we do because we have a terrible feeder. What feeder are we using for these tests? Well, it's a belt, right? So we put a hopper on a belt, some pellets fall out, right? Now over here is, 1 pellet fell out. And over here, 2 pellets fell out. Over here, 5. But there are lots of times where there are no pellets falling out. And this is a small machine. I mean, how many pellets are in the first channel of a 1-inch screw? This is a big change in mass variation. And over here, what have you got? A rather unsophisticated control for the speed of this belt. And where is it running? It's running at about 11 or 12% of maximum, which is not where a motor should be run. Motor should be run to be effective at a much faster rate, 50, 80, 90%. Remember this is, inexpensive. It doesn't even have a tax feedback loop. So you're just not going to get very good variation. But this still gives us plus or minus 30 pounds. Now, how do we know that we're in tetherball mode? How do we find that? Well, one of the control panels. And basically, it's pretty simple. We've got a typical barrel pressure gauge, transducer downstream, and we've got something upstream. We want this one to say low. Low means 0. That's what we want. Because we know that there's no pressure whatsoever in the channel. So if we've got our screw balanced correctly, then what we do is we set the RPM too high. That says 95 RPM. And we know it's too high, we don't care. Then what we do, we get the feeder set, so just leave that alone. And we just work with this RPM. What we do is we watch this, and we watch this. Slowly, we bring that 95 down. Because at first, when it's too fast, it'll keep surging and it'll get a big drop in pressure because you're not filling the metering section. But as you slowly reduce the screw, the feeder starts to catch up, and sooner or later, you get to that plus or minus 30 pounds. That's all there is to it. That's all there is to getting this to work, that plus or minus 30 pounds. Just slowing it down. You don't want this to go up. You start seeing pressure there, that's bad. Because then you fill things up beyond the capacity of the screw, you start to get pressure. Now I wanted to share with you some pictures of the results. So on the left, what are we looking at? We're looking at low density polyethylene, which is not hygroscopic, but we're putting into it coffee chips. Why? I don't know. Customers bring us all kinds of things, right? The coffee itself turns out to be hygroscopic, which is not surprising. And it also has an oil in it. Right? Now, we did a lot of work on traditional vents, and in 5% coffee chafe, we needed 2 vents with a vacuum to get all the bubbles out on the dry coffee chafe. So the only thing that was in there was the oil at that point. Went to 7.5%, we couldn't do it, with 2 vents on the extruder. So, we put the molecular homogenizer screw in, and, we started out with excessive feed. What you're looking at here is foam. It's a really bad foam, too. Okay, so we've got the molecular homogenizer screw in there, but it's not working. What did we do? Well, we just started more. And we go from this to that, and very fast. Now, there's not a bubble to be seen, obviously. Well, that's an interesting thing, because we took out oil. It's not just water. Oil is a bigger molecule than water is. Right? So we sequestered it, which is the word I like to use. We took that oil and we put it in such a way you can't see any bubbles. Here's a PVA copolymer. So a customer came to us, he's got PVA, and he wants to do reactive extrusion. What is reactive extrusion? Well, you put something in with the polymer, reacts with the chain, turns it into a gas as part of what happens. Right? So you gotta get the gas out. Well, first of all, he brought us undried PVA, and we ran it. And, there's the undried PVA, and again, there are no bubbles in it. That's what you would like. But I mean, it's really clear that there are no bubbles, and that's our measurement system right now. So what he really wanted to do was, put a metallic organic in. Here's our feeder, you can see some of the pellets falling off right there. And he's put in 3% of the metallic organo material, which reacts. And when he did that, we got no bubbles. It turned a little white, sure, but you put something else in, a lot of things turn white. Then we put in 6% of the metallic organic, and it's foamed. This was what he got when he put it through his machine, and it's pretty badly bubbled. So we wanted to solve this problem, of course, because he wanted to do more than 6%. So we took one of the vent plugs out over the molecular homogenizer and just did an atmospheric vent. When we did the atmospheric vent, at that point, no bubbles. 9%, no bubbles. 12%, no bubbles. He did some simple microscopy and sent us some 9, and 12%, and there's no bubbles. What he told us was he believed that at 12%, we might have converted 1.5% of the chain to a gas. That's a lot of gas. PMMA, it's 0.3%. This is how much water it absorbs in water vapor. So, and this is just an atmospheric vent. But think of all that surface area, right? Think of that cone going around, exposing more surface area. Think about that stretching of the film underneath and looking up. It's a big film. It's 1.4 mils. How easy is it to get the gases out? Right? And you're going to do it again and again and again and again.
In a couple of minutes.
When you say a couple minutes, do you mean until 25 or do you mean until 30?
You're already past 25.
Yesterday, you caught me off guard. All right, we can go through these fast. Here's color concentrate. Color concentrate has water from the sand, as hydroscopic, and it's got surface moisture from the white and the black. You don't know what bubbles look like? That's what bubbles look like when you're making a film out of it, right? So we put it to the homogenizer. You don't see any bubbles. We take those pellets that we made, put it into a conventional screw, and we don't see any bubbles. Listen, we can do direct extrusion. The Twin Screw guys like to talk about that. We just put it on through the molecular homogenizers, which is acrylic, and that's as clear as gas. We can take it out and put it in the conventional screw over here, and there's no bubbles after 3 days. Polycarbonate, PEEK, the answer is no bubbles. PET undried, no bubbles. Get tired of saying no bubbles. We took those pellets, which are now in the amorphous form, put 25% of them in over there, no bubbles. We took foam. This is a different thing because we flood fed it. So the customer determined about 1.5% was required in these operations. We got the chemical blowing agent down to 0.5%. I was close.
Good.
All right.
We have time for some questions. David, can you come up here with the presentation?
So in the case of, say, like the polyester, you've got the dissolved water in there and you put it through, did it change the physical properties of the polyester? No, chain scission issues?
I made a
Molecularly?
big deal about this yesterday.
Yeah.
Okay, we're in the R phase of R&D.
Okay.
Okay? However, since you mentioned polyester, we've got two things that we're gonna be doing. One is we've got Peloton now, and I've got somebody who will test them for me, and we've also got Reclaim.
Yeah.
Reclaim's a whole separate interesting subject. We're gonna do them both.
Yeah.
Anything else? Yes, young lady.
So you mentioned some different materials that you've already tested. Do you have some kind of plans in your future for testing some different materials? And if so, what would those be?
Well, there's PLA, right? That has interesting, obvious applications because if you can keep it dry, people will like their 3D printer rod. We want to start working on the vinyls because that has no oil in them. We think it might have advantages if we mix that oil better. We've got some particular things that are going on. Flame retardant things. So that's a big deal too, because so far we've concentrated on small. Sooner or later, big has to happen, and that's what we're working on too. Anything else? Oh, backwards.
How many gigawatts does it take to run that thing?
That is a great question.
Is the specific energy higher or lower than,
I can give it to you this way. An empty screw runs at 5.6 amps. Perfectly clean screw empty, 5.6 amps. That machine's got a maximum of 13 on the 5 horsepower drive. All of these things run between 5.8 and 6.1 amps.
so that's elongation going on?
Apparently. Yeah. Yeah, it's all elongation. Yeah.
10,000 pounds an hour.
Pardon me?
You were probably running at 10,000 pounds an hour.
No. I said R. It's R of R&D. We have to go to D next. We're just working on D. But look, I gotta tell you something. Suppose you're doing 4.6 pounds an hour, which was the polycarbonate stuff. If I'm producing 4.6 pounds an hour of diamonds, I'm one happy camper. Well, what are the possibilities here that you can do things? I mean, lots of things run at low output. We may not ever have to get to high output to have a big thing going on.